Today we're going to talk about memory subsystem. Here are the things we're going to cover in this lecture today. We're going to give an overview of IA or x86 memory and software architecture, and then we're going to talk about different memory types. And after that, we're going to discuss interfacing to memory subsystem. And at the end, we will talk a little bit about virtual memory. First, I want to show you two different ways to organize memory and I/O devices as part of your embedded computing system. The first way to organize memory and I/O devices is so-called isolated memory and I/O. What you see here is a typical x86 or IA architecture based embedded system. You have a microprocessor, and on the left you have your memory subsystem, and on the right you have the I/O subsystem. You can put these two subsystems into two separate memory space. By memory space, we mean it's a addressable region, and starting with address 0. So when you put the memory and I/O in separate address space, and they both have starting address 0 and up to their maximum address, depending on the size of the space. So what you see here is, to both of these address space, you need to provide address, also data connections, what we call buses. In the memory subsystem, or in the memory address space, you can have program content, you can also have data. Whereas in the I/O subsystem, you have data. The second category is so-called memory mapped I/O. In this organization, you have one single address space. And this address space is connected to the microprocessor. In this memory address space, there are certain regions that you can reserve for I/O devices. So the way to access these I/O devices, or part of the I/O subsystem, you can use some special addresses. So overall, by looking at the address, you don't really know it is a real memory chip or is mapped to a I/O device. Okay? So these two ways of organizing memory in I/O devices are different. They have advantages and disadvantages. In the first isolated memory in I/O, the advantage of doing this is you have a complete memory address space, right? You don't reserve certain regions for I/O devices. You have the whole memory address space, which you can use to access memory chips. Whereas, on the other hand, this memory mapped I/O, part of the address space is going to be reserved for I/O devices. So the whole region cannot be mapped to or used by memory chips. But the good thing for the isolated memory I/O is that because they are in separate memory regions or memory space, you do have to use different instructions for accessing content from memory or I/O. So you have specialized I/O instructions. You do in or out for x86 processors to access data in the I/O subsystem. And you know what data you're going to access. Is it going to be a data stored in memory, or is it going to be a data stored in I/O space? So you can do sort of optimization in terms of the interfacing for these two different systems. For this memory mapped I/O, the benefit of having this is that you don't have to use separate I/O instructions. You treat these data in a uniform way. You only need to provide an address, and you don't care where these data are residing. So that was the big picture. So now we're going to look at individual memory component. This is a very typical memory chip that you may use in your system design. There are a set of pins called address pins, usually numbered from A0 through AN. So we have N plus pins used for address, N plus 1. On the other hand, you have output, or in some cases, input or output connections. These are data pins, and represented using O0, O1 through ON. At the bottom of this chip, you see there are two control signals, CS and OE. CS stands for chip select. OE stands for output enable. Chip select is oftentimes active low, which means that if you want to have this chip to work, you need to put a logic 0 to CS. For OE, this is for outputting. So essentially, if you are reading data from this chip, from this memory chip, you need to do output enable. And often this OE is also active low, so you need to put a logic 0 to make this chip to output data, to perform the read operation. WE is write enable. If this chip is writable, then you won't have to have this write enable as a control pin, basically to tell this chip that whether you need to perform or when you need to perform write operation. For memory chips that are read-only, you don't need this write enable because you don't perform write operation. Also, the write enable is often active low, so you need to have a logic 0 to perform the write operation. There are many different kinds of memory components or memory chips. Read-only memory, programmable read-only memory, erasable program-only memory, electrically erasable program-only memory. So the first several of them are belonging to the read-only memory. And the second category is the random access memory, or RAM. And these memory chips are both readable and writable. And it has two different kinds, SRAM and DRAM. And within DRAM, you have different subtypes, each with different performance. SRAM stands for static RAM, and DRAM stands for dynamic RAM. Flash memory is a third type that has some unique features. These flash memory chips, they are non-volatile, which means that they can retain information after you power off the chip. But on the other hand, if you want to store new information, you need more time to erase than the random access memory. First, we want to look at erasable program memory. So this kind of read-only memory, in normal operation, they can only be read. So there's no write enable control pin to this type of memory. But before you have this ROM chip in your system, you really have to program it so that it has the initial data which you don't expect to change for a long time. And in that case, you need to do the programming part. And to program such chips, you usually need special tools or special circuit to put this chip into programmable mode. And oftentimes you're gonna have different operation voltage applied to this chip. Also different control signals applied to this chip to put into a writable mode, and you perform the initial write operation to it, to write the initial data to this ROM chip. After the initial programming phase, the information that you write is going to be returned in this chip, and you can take this chip, put it into your system for normal operation. This chip is typically used for BIOS, for firmware that you don't expect to change often. In this particular chip, this is a 2716. That's the model number. It is a 2K times 8 EPROM. Now, we often use this representation. This is to say this chip outputs 8-bit data, and it has 2K locations. So essentially, this chip has 2K bytes stored as the content. So what you expect to see is this chip, if you look at its physical shape, it has to have 8 pins for data, because that's the data width. So you will expect to see out of the pins coming out of the chip, at least there will be 8 of them that are used for data connections. For the 2K, so that's the size, that's the number of locations in this chip. Now if you do a simple math, choose the power of x equals 2K. What is x? It's going to be 11. Okay? That is to say, you're going to have 11 pins used as address for this chip. That's how you can select 2K locations. So if you look at this diagram, this pin configuration diagram, you can find that from A0 through A10, you have 11 pins for the address. From 00 to 07, you have 8 pins for data. And of course, this pin has other control signals, power and ground, and you have chip select. Also, you have this PDPGM. This is a special pin used to program this chip at the very beginning. Can you repeat your question?
It has more outputs than inputs, right?
If you're talking about data, there's no input data, because this is the read-only chip, so it only does output. It takes control signals, chip select, for example, to basically put this chip into operation mode. Now in this slide, the bottom right figure shows the internal organization of this chip. There are some decoders, X decoder, Y decoder, are used to decode the address, so that the address will be able to select one of the locations in the chip. And you have this 16,000 bit cell matrix. That is the transistor cell used to store the bits. Also, you have output buffers to drive the output. Now we have more details about this chip, which I will not go over that many. This picture shows first the some timing parameters of this chip. And the bottom half of this slide shows you the waveforms. Here we can see that address, chip select, and output, those are the major signals coming out of the chip or going into the chip. The first signal showing up in the timing diagram, this is the address. And the second one is the chip select signal, and then the bottom one is the output. Now, the way to read this timing diagram is that for single line signals such as chip select, basically this line shows the logic high or low of this signal. For multiple line signals like this output or this address, if you see a single line, that means during this time period, this set of signals are invalid. And if you see a shape like this, as a box, that means this is when that set of signals are valid. Okay? So what we see from here, this timing diagram example, if you start counting from the moment this chip select signal becomes 0 till you see a valid output on the data line, there is some delay. Okay? This is the delay by design coming from this chip, because the chip, the internal circuits, has to respond to all the control signals before the valid data can be sent out onto the data bus, onto the output. So this is the delay showing up here, TCO. This is the chip select to output delay. So what is showing up in this table is that the max delay is 120, I believe this is nanosecond.
Does it sound like output because it's an active one, and when the chip select goes to 0?
Yeah, so this chip select functions as a read control signal. So when you do select this chip will output data based on the given address. Okay. And this 120 nanosecond, that's the maximum delay time. So as part of your design, it is safe to assume that after this 120 nanosecond, you will have valid data on the data bus. But it is not safe to assume that after, say, 90 nanosecond, you will see the valid data. Okay? So for designs that you have multiple chips operating at different frequency, you have to be careful whether the action of the next chip can tolerate or can anticipate this maximum delay. Now we want to look at the second type of memory chips, RAM chip, and in particular this is the static RAM. in this example, we're looking at a TMS 4016 chip. And we know that from this 2K times 8, this chip has an 8-bit output. And again, it has 2K locations. So you will expect to see 8-bit data bus and also 11-bit address bus. Because this is a RAM, that means we can do read and write. So you expect to see a output enable and then also write enable. So that's what's shown up here in this diagram. Yes?
Can you explain when you organize the thing in this way? Remember why they don't, well, you know they don't fit on one side, but is there some kind of general explanation, or it just depends on the design?
Well, this largely depends on the actual design. Depends on the layout of the chip and the packaging. Yep. Let's count. So we should see 11-bit address. So we count from A0 through A7, and there's some other pins spread out here, A8, A9, and A10. So total, you have to have 11 pins. Also, as part of the datasheet for this chip, you will see these explanations of these signals. Output enable, chip select, write enable. The symbol used for each chip may slightly different, but they all have to have these functions: chip select, write enable, output enable, in addition to the power and ground. The next type we're going to look at is the dynamic RAM. Dynamic RAM supports both read and write, but because of the design, it's different from SRAM, where we use 6 transistors to store a bit. In DRAM, we just use 1 transistor to store a bit. Because of this property, the DRAM has a unique feature. It retains data only for 2 or 4 milliseconds on this capacitor. As a result, in order for DRAM to operate correctly for a long time, it needs to be rewritten, or so-called refreshing. So you need to periodically recharge the cell, the capacitor, to retain the content. So that's one unique feature, well, characteristic. It actually leads to complexities in operating DRAM, because you need to consider this refreshing cycles. The other challenge DRAM has to deal with is the address pins. Now, the benefit of DRAM compared to SRAM is that it has higher density. For a given number of transistors, you can store much more bits in DRAM than SRAM. But that comes with a cost. Whenever you have more bits, data bits stored in the chip, you have to consider how you're going to access these bits. Okay? When you have more bits here in a chip, that means you have more memory locations. Not 1 time or 2 times more, it's many, many times more bits than an SRAM chip. So let's consider this example. Let's say we have 64K by 4 DRAM. That is to say, for this DRAM chip, each data element in this chip is 4-bit. Okay, so the minimal unit you can access is a 4-bit out of this chip. and you have 64K locations. Okay? With 64K locations, how many address bits you need to use to access each one of these locations? There'll be 16, right? Because 2 to the power of 16 equals 64K. Think about K is a 2 to the power of 10. Okay, you have another 64 times, so that's another 6. So total, to access these 64K locations, you need to have 16 pins. Okay, now this math is simple, but adding more pins to a chip turns out not that simple. Okay, there are many challenges in terms of packaging, how you route the signals out of the silicon area to the outside. And when you have higher capacity, let's say you have 1 meg locations, and that's 20 pins required. So this number can go up very easily. So to address this issue, DRAM designs often use split address pins. The way it works is that, for example, this 64K locations, we need conceptually 16 pins, but physically we only use 8 address pins. Okay, how is that possible? If you have only 8 address pins connected to this chip and you want to access 64K locations.
So, one address can do 2 different things.
So we essentially do time multiplexing. So this 16 address lines are divided into 2 halves. So one half has 8 lines. We supply the first 8 in the first cycle, and then the second 8 in the next cycle. And we give them names. The first 8 is called row address, and the second 8-bit address is called column address. Okay? So, as we explained here, these 16 address lines are divided into 2 halves. We use 8 address pins in 2 8-bit increments. As a result, we need to have separate control signals to indicate that whether currently these 8 pins are row address or column address. So what you see is here we have 2 special control signals called column address strobe and row address strobe. And often the column address strobe is also chip select. So if you look at this DRAM chip, it has address inputs, address signals from A0 through A7. For data, we have DQ1 through DQ4, a 4-bit input and output. And of course, we have write enable, we have power and ground. Here's the timing diagram that shows you how this chip operates by using these 8-bit address lines and row address strobe and the column address strobe. So what we see here in this timing diagram, we show row address strobe, column address strobe. Both of them are single line signals, so you will see either it's high or low. Okay. For the address from A0 through A7, and these are a bundle, a bus. So what you see here is sometimes it's invalid, sometimes it's valid. So the way it operates is that first you put the address, the row address, on this 8-bit address bus. And then you assert, which means you're gonna turn this row address strobe from 1 to 0 because it's active low. So that's an indication that right now the value on the 8 address lines are the address for row address. And after a certain time, the control circuit gonna put the column address on this 8-bit address bus, and then assert, which means gonna turn the column address strobe from 1 to 0 to indicate that currently this is a column address. And once that's done, after a certain time, this memory access will complete. Because the chip has both the row address and the column address internally, so together it has the 16-bit address it needs to access the data. Sometimes these multiplexers are used for DRAM access. What we see here is 2 multiplexer, 2 to 1. This one, as you can see, we have 2 channels, A and B, and we have 8 inputs and 4 outputs. Depending on the control signal here, this chip will select one of these 2 channels, either A or B. For example, if I have a 0 here, then this 1A will be outputting through A0, 2A will be outputting through A1, and so on. If this changes to 1, then the other channel will be outputting. So what we're seeing here is we are using this row address strobe to connect both of these, the control bit for this multiplexer. So based on the value on row axis strobe, one of the 2 channels will be outputting. So you are dividing these altogether 16-bit address into 2 halves, okay, based on the value of RAS. So it's either A0, A1, all the way through A7, or A8, all the way through A15. As we have very high density on the DRAM chips, if you want to build out a memory subsystem, oftentimes you need to employ multiple DRAM chips. For example, here, what we're showing is so-called single inline memory module, or SIM. On this PCB board, we have 9 DRAM chips, and each of them is a 4 meg by 1. That is to say, for each of this chip, it has 4 million addresses, and each of them will address 1 bit. So out of this one chip, you will have 1 data bit, and you will have many address lines. You can calculate how many. How many address lines for this chip? So that is to figure out 2 to the power x equals 4 million. So that's 22. Conceptually, you need 22 address bits to access these 4 million locations. But because of the row access and column access, you essentially have 11 bits for the address to this chip. So altogether, we have 9 of them. Now the reason we have 9 is, well, you know we have 8 of them for a byte, right? Because each chip will output a bit. So together 8 chips will output a byte. The 9th one is used as error checking. It's going to do the ECC error checking to verify whether these chips are outputting the right data or not, any corruptions happen or not. And on the other, on the right side, this is another design where we have a different, slightly different organization. We use a different DRAM chip, and each of them here is a 4-bit. So together we have a 32-bit data bus for this chip.
So you see the 9 is used to do error checking?
Yeah. The 9th is used as error checking.
22 divided by 11 because as a multiplexer.
Uh-huh.
And the 9 is used to
Now, after the single inline memory module, people have been using dual inline memory module, which has higher density. This is especially for modern computing systems where 64-bit data bus is required. So it has 2 sides. So if you look at from the side, you see this PCB has 2 sides, and each side has a number of memory chips. And for this particular one, on one side it has 84 pins, and 2 sides they have independent pins. So together you have 168 pins out of this DRAM chip. I mean the dual inline memory module. Flash memory is very popular nowadays because it can return information even after powered off. The benefit of using flash memory is that it can support very fast read speed, but on the other hand, if you want to update the content to perform write operation to these flash memory, the speed is quite slow compared to the read. It requires different voltage to erase and write data. The older ones require 12 volts, and newer ones use lower voltage. The operation is similar to SRAM, where you have these control enable, chip select, output enable, write enable, etc. I want to give you an example of double EPROM chip where we use a slightly different connection from the previous ones we introduced. This figure shows one way to connect these double EPROM chips onto a serial data bus. We will talk more about this serial interface in the next lecture, but I just want to bring up this as an example to show you how memory chips can be used in different ways. What we are seeing here is essentially 2 double EPROM chips. Okay? And first, you can see here these 2 chips, they are identical. And in order for them to operate, they have to be connected to power, of course. So that you can see VCC is connected to the VCC to both of them. And ground is connected to the ground. The Second thing I want you to look at is the address. Okay? This A0, A1, A2, you can see they appear on both of them, but the way we connect these chips are different. For the one on the left, we connect A0 to the VCC. A1 and A2 connected to ground. Okay? In comparison, the chip on the right is connected in a way that all of these three address pins are connected to ground. So if you give a code based on the voltage, the logic level, this will be 1, 0, 0, and this will be 0, 0, 0. Okay? Now keep in mind, these values are later be used to identify the chip. The other signal I want you to pay attention is this clock, okay? Serial clock, and this serial data. Clock is to supply a clock signal to drive the operation of the chip, this memory chip, and data is connected to the data line. Now, since we're talking about serial connection, so we only have 1 bit data. Okay? Now, once you see this kind of connection, you have 2 chips connected to the same serial data line, and you need to figure out several things. First, how do you say I want to talk to a chip on the left rather than chip on the right? Okay? So that's one thing you have to think about if you want to access the content of these chips. The second thing you want to figure out is, for each one of these chips, it contains a lot of data. Now, what's not shown here is that internally, this chip has many locations to be accessed, even though the output is only 1 bit at a time. So the second question we would like to answer is, how do we tell the chip that which memory location we need to access? Okay? For the serial data transfer protocol, this is how it works. We're giving here 2 examples, actually 3 examples. The first one is write address. Before I explain these individual bits, I want to just briefly mention that in order for this serial connection to work, we have some special control signals, and these control signals are implemented through the clock. And we conceptually represent these control signals as start, acknowledgement, and then here stop. You don't have to know exactly the details how these special control signals are implemented at the circuit level, but just want to mention to you that we do have these special control signals in order for this protocol to work. So what's happening here in the first example is that after the master or the microprocessor put out a start signal, it will then output a special code, this 1010, followed by A2, A1, A0, and then a 0. Now, this first 4 bits, well, these are coming from the bus, the data bus. Okay? everything is going into the chip or coming out of chip through the data bus, the single wire, the serial single wire. So these bits will appear on that single wire. This 1010 is the indication of this is the access to double EEPROM chip. Although in our circuit we only have double EEPROM chip, but you may have cases that on that same bus, same data line, you connect other type of chips. It's very possible. So this 1010 is an indication that I'm going to access double EEPROM chip. And then this A2, A10, if I go back, is the value for A1, A2, A0. So for our case, if those 3 bits are 0, 0, 0, that is to say, I want to access the chip on the right. Why? Because that's how we identify this chip. If those 3 bits are 0, 0, 1, that's to say, I want to access the chip on the left. And this ACK will be the response from the double EEPROM chip. And after that, what follows are the real address to the content stored in that chip. So don't confuse these A2, A10 with this A2, A10. These from A0 through A14, these are actually the real address to access content within that double EEPROM chip. Okay, so with these series of ones and zeros, we are trying to say, I want to access double EEPROM 000, and this is the address I want to access. Okay, so this is to give the address to that chip. And following that is we expect the chip to respond with data, and that's what happened in the second phase. So the chip will output. Well, before the data comes out, again, this is the control bits coming from the master device who initiates this read operation. Usually this coming from the microcontroller that wants to read this content. So again, send out this 1010 to identify this is the double EEPROM chip. I want to access the double EEPROM chip, and I want to access this particular one. Then that chip will respond with the real data. And these data, again, coming out of the chip one bit after another because this is a serial bus. Or if it's a write operation, the new data is put out to the data bus directly after the first write address. Okay, so this is just give you example of different ways to connect the memory chips to your system. We will have more detailed discussion about the serial interfacing in the next class.
What's the difference of the first A0 to A2 and the second A0 to A14?
Okay, so this A1, A2, A0, this is the identifier of that chip. Let me go back to this previous slide. So the first A2, A10 are used to identify one of these chips. And once this chip is identified, the next series of address bits are used to select content within this chip.
So there should be another 15 pins on the chip.
Well, not 15 pins, because the chip will take that 15 address bits through the same wire, because this is the only wire that has, you can talk to the chip. This is SDA, this is the serial connection. So all these address bits coming through this pin into this chip to select a location within that chip. Yeah.
The stop acknowledge they're on the same serial bus, or is some kind of
It's on the same serial bus.
it's just the one.
It depends on its combination of the control signal and data signal. So they have some special signals treated as control, special control bits. The next topic we're going to discuss is the address decoding. Now, think about that you have such a microprocessor and you have certain memory chip that you want to connect to. We take this simple example. For this 8088 Intel microprocessor, it has 20-bit addresses. That means it can access 1 megabyte of address space from 0 all the way to FFFFF. For this EEPROM chip, the 2716, we know it's a 2K by 8, so we have 11 bits for the address. So on one side, the microprocessor thinks that it has 1 megabyte of address space. It can access this large range. But on the other hand, if you have only this 2716, this chip, it can only provide 2K content for this microprocessor. And depends on where in that address space you locate this EEPROM chip. If the processor supplies the correct address, it can access the content. Otherwise, it will access something that's not there. Okay. So for this case, we know all of these 20-bit address from the microprocessor. That is to say, we have address bits from A0 through A19. We can certainly connect the lower 11 bits directly to the chip. So 20 minus 11, what about the upper 9 bits? What do you do with them? We should decode the other address bits properly. Otherwise, you will supply your microprocessor with some invalid data, some garbage data, because it doesn't know, or you don't have something valid to put on the data bus for the processor to read. And here comes the concept of decoding. We need to connect the address pins that do not connect directly to memory components. We have example in this figure. Here we have memory chip. This is a EEPROM 2716. It has 11 address bits from A0 through A10. It has 8-bit output. It has an output control, chip select, and then power. On the left side here, these are the signals coming from the microcontroller or microprocessor. The microprocessor, in our example, has 20 address lines, so you can see from A0 through A10 and then from A11 to A19. Also, it has control signals coming from the microprocessor. Read control, so if you have a 0, you're gonna do the output enable for this chip. The other control signal is this IO/M bar. This is a control signal to tell the subsystems outside the microprocessor whether this is the I/O operation or a memory operation. So if it is a memory read, okay, if you do, let's say, move AX comma bracket BX. Okay, picture that. This is a typical memory operation, memory instruction of the Intel x86 instruction set. If you have such instruction, eventually this microprocessor will output 0 on this control bit to indicate that this is a memory read operation. Okay, we are using here a NAND gate to perform this decoding. Although in the next few slides we're going to talk about a different way of doing the decoding. Nevertheless, in this example, what we do is we use this control signal going through a NOT gate here with the inverter, and then connect that output to the inputs, 3 inputs to this NAND gate. The rest of these input pins to this NAND gate are connected to the rest 8 address pins. Okay? And then output of this NAND gate is connected to the chip enable signal. So let's see what will happen if we are going to read, or if the microprocessor is going to read this address, FF800. If you write this number in binary, you can easily find that for this address, the upper 9 bits, the most significant 9 bits, are all ones. That is to say, all these bits, all these inputs to the NAND gate are ones. Also, at the same time, because this is a read operation, so this is going to be a 0. Okay? And it's a memory read, so this is going to be a 0. You have 0 as the input to the inverter, so you have 1 coming out. So you have all ones on these 13, 14, these inputs to the NAND gate. So what's happening here is all the inputs of this NAND gate are ones. So you have a 0 as the output. So you have 0 to the chip enable. You also have a 0 to the output enable, and you have the valid addresses for the lower 11 bits. So this double EEPROM will work, and it will output a data. Okay? And for other addresses on the upper 9 bits, it will cause this NAND gate to output a.
Because it's 1 0 0 0.
Because if any of these 9 bits are 0, this NAND gate will output a 1. And in that case, this chip will not work. So the output will be put into high impedance. Essentially, the microprocessor will see nothing on the data bus. There will be no valid data on the data bus. Using NAND gate is a very simple way to do the decoding, but we do have other approaches. Here we can use a 3 to 8 decoder. This example, this is the 74LS138. This is a 3 to 8 decoder. On the input side, we have selection inputs, CBA. Also, we have enable inputs, G2A, G2B, and G0. The way this chip works is that we, of course, need to have these chip to be enabled. So you're going to have 0, 0, 1 on these control bits to enable this chip. And then the output is going to depend on the input value on the CBA. And this is the truth table here. So this is the, from this row all the way to here, this is when we have this chip operating as a decoder. And depending on the input, only one of the output is a 0. The rest of the bits are 1s. Okay? So that is to say, using this 3-bit input, you can select one of these 8 outputs, and only one. Now here I want to give you an exercise. And the problem description is as follows. Suppose you will be given enough this 2764 EPROMs. And we want to build a 64K by 8 section of memory starting from this particular address. Assuming the number of address bits is 20 in total. So let me repeat the problem again. So suppose you will be given enough this 2764 EPROMs, and I would like you to build a circuit using these EPROMs and any necessary 3 to 8 decoders or NAND gates. I would like you to build a 64K byte section of memory starting from this address. There are some hints given here. The 2764, this EPROM has 4K bytes. Okay, so 4K by 8. Now the first question you want to answer is how many address bus? How many address bits on the address bus? And assume that the signals coming from the microprocessor include the address bits, read enable, and you can use 3 to 8 decoders. Okay. Now you can take a piece of paper and draw a schematic on that, and we'll come back in 20 minutes.
Taking a break.
Yeah, we're taking a break.
So about the group,